So we're going to learn about oxidation numbers. An oxidation number is a technique to keep track of the electrons gained by the reduced substance and those lost by the oxidized substance. So without actually having a very, very simple mathematical way of telling what's losing, what's gaining electrons, we couldn't just look at it, look at the formula, the chemical formula, and tell this is oxidized, this is reduced. So we use a very, very simple technique, also referred to as the oxidation state. So if you ever see it as oxidation state, it means the same thing. We're going to use oxidation numbers. And I usually like to say OX number just like that. Now, a word of caution before you begin. This overlaps with a charge, the electrical charge, like for example, you had sodium plus or chlorine or chloride Cl minus. It does overlap to a great degree, but it's not the same thing. It is not the same thing because you can have oxidation numbers in compounds, unlike the charges that you've seen on elements. So that's the idea that you want to keep in mind. And then also one more thing is that this is again, it's a technique. So these are imaginary numbers. They help us. They help us determine what's being oxidized and what's being reduced. Very well. Now, there are a few rules here that you need to keep in mind. Luckily, the overwhelming majority of these you know already from ions and simple knowledge of charges. So nevertheless, you still need to go through them and practice. And again, there should be no issue. So let's begin. The oxidation number of an atom in a free element, simple word is elements, just elements, is 0. So they have an oxidation number of 0. So if you ever see an element by itself, well, that has an oxidation number of 0. What is an example? Sodium by itself. By itself. Usually put a solid after it. Lithium. Iron. Copper, etc. And of course, remember your diatomics. So if you see hydrogen gas like this, that's an element. If you see oxygen gas, O2, that's an element. Again, by itself, F2, etc. Of course, 3L2. So I'm giving you some examples. How would these look like in a reaction? We're going to get to them. They would look like this. You would see, like you have one substance, and then you'll see plus, for example, O2 by itself. This is not the same as, for example, something like CO2. This is an element. This is not an element. So be careful. It has to be by itself. That's why it says a free element. The oxidation number of monatomic ion is equal to its charge. Well, if you have sodium plus, that indicates that the oxidation number is +1. So just look at the charge. If I have Fe +2, well, what do you think is the oxidation number? Yes, it's a +2. If I have N -3, once again by itself, then again the oxidation number is -3. So that's it for monoatomic, one atom, just one atom. So you always look at the top here, and if you see it, then that's your oxidation number. Now, now we're starting to talk about molecules and compounds. So now we're no longer talking about ions on their own or elements. We're talking about compounds and molecules. So those are collection of atoms. The sum of the oxidation number of all atoms in a neutral molecule or formula unit is 0. So if I have CH4, the sum of the oxidation number is 0. Why? It's neutral, so there is nothing over here. There is not a 1 over here. This is neutral. So if I have now something like NaNO3, once again, this is a neutral molecule or formula unit. This is a formula unit. There is nothing over here. So the sum is 0. It's 0. Again, you got to look there. However, if you have an ion, now you have to look also at the top right-hand corner. And if you see a charge, then that's going to be your sum of the oxidation number. That's the total. So in this case, if I have something like NO3 minus, notice the difference now. It's no longer, because probably know why. So then that has a sum of the oxidation number It's a polyatomic ion. Of negative 1. Right there. That negative 1. Of course, if it says a negative by itself. If I have something like Cr2O7 minus 2, once again, the sum of the oxidation numbers would be a minus 2. Right there. So that's where you look all the time for the sum of the oxidation number. Now, we will talk about dissecting. Now, this video is a little bit longer because I kind of want to finish all of them. And in this case, now we talk about the group numbers inside their compounds. So group 1 metals, that's group 1, the alkali metals, that's lithium, sodium, potassium, etc., cesium, etc. All of those in a compound, they always have a +1, always have a +1 oxidation number. What do I mean? Well, we just talked about NaNO3, so it should not be any doubt in your mind that that is going to be a +1 for sodium. It is group 1. It's going to be a +1. Here's another one. If I have Li2SO4, you might say, well, I have 2 of them. Sure, you do have 2 of them, but each lithium, of course, we're going to learn about how to find those numbers individually. Each Li has a +1. Now, of course, you have two of them, so it's going to be a total of +2. So again, the group 1 always have +1. Group 2, so that's beryllium, magnesium, calcium, etc. They always have a +2. Look at the periodic table. They're in your ion sheet. No need to really memorize anything. They always have a +2. So if I have something like MgO, that's always a +2. If I have CaCO3, once again, that's my group 2. That's a +2. Again, I'm talking about the group 2 metals. Now, the oxidation number of oxygen is always a -2, except in peroxide, and we're not going to deal this much with it, where it's -1. So these are special cases. But anytime you see O2, or O, I'm sorry, O, then that's going to be a -2. So if I have CO2, then you know for sure that each O is -2. The only examples you deal with peroxide is really just this. Just keep this in mind, is H2O2, where actually each O is -1. So that's hydrogen peroxide, at least at this level of this course. Even in MgO, the one we just talked about, it will be a -2. Once again, O is always a -2. Be careful once again about O2 by itself. When O2 is by itself, we said that this was an element. So this would have an oxidation number of 0, 0. So be very careful. The oxidation number of H is +1 when bonded to a nonmetal, -1 when it's bonded to metals. Very well. So if I have something like HCl, H is going to be a +1. Let me make the +1 more explicit here. So it looks like another H. This, let me use a different color. +1, because Cl is a nonmetal. However, if I have something like NaH, then my H will be a -1 or a -1, because Na is a metal. So this becomes a hydride in this case. Getting close. Oxidation number of F is -1 always, unless it's F2. However, other halogens, Cl, Br, and I, have oxidation numbers of -1. But when bonded, these three, when bonded to O, they have positive oxidation numbers. So if I have Cl, Br, and I all attached to O, then they will have positive oxidation numbers. But if I have Cl attached to here, in this case, something like HCl, then you just go by the -1. So H in this case will be -1. Or if I had something like NaBr, that's not an O. All right, let's see why. That's going to be a -1. So the moment we will get to these right here in iodine, where they actually will become positive oxidation numbers. And lastly, before we end and then look at the video on the examples, is since those are set in stone rules, what's left is that you will have atoms that are changing. They change all the time, like carbon, nitrogen, phosphorus, silicon, boron, and metal atoms, including the transition metal atoms that can have positive oxidation numbers. And they are not the same as the charges. So those are the ones you're going to have to solve for them. And I will show you, we will go through them when we get to the practice. So very well. Digest those rules, understand them, and of course, you may start before you watch the next video if you would like to practice.